This tape is going to deal with another technique of integration. This technique is called change of variable. As in many other cases in mathematics, oftentimes we want to perform a certain task, but the expression with which we're dealing is too difficult to handle. So we try to change it. We try to actually put it through a transformation, changing it in some way so that the task we want to undertake will be made easier. Having completed the task, then we reverse the operation, we reverse the transformation, and put it back as we found it. Now, this is not an uncommon procedure. You're going to see it several more times in calculus and in differential equations. The transformations that you see will differ from time to time, but the idea of changing something so that it's made easier to handle is consistent throughout calculus and differential equations. Let's look at example number 1 on your worksheet. We're interested in finding the antiderivative of dx over 1 plus the square root of x. Well, at this particular point, try as you might, you cannot force this into any one of the forms that you know. It doesn't fit the power rule. It doesn't fit any of the singular forms that you've memorized. And so in order to find the antiderivative, we really don't know what to do. We're stymied at this point. Well, one thing that we can do, the item that seems to be giving us trouble is the square root of x. And so we might think to ourselves, if only the square root weren't there, then perhaps I would have a chance to take the antiderivative. Well, that type of thinking leads to a change in variable. If x were replaced with something that had a perfect square root, then we would be able to get rid of the radical. So we replace x with something that has a perfect square root. So we're going to replace x with u squared. But the one catch is this. If you replace x with u squared, then you must also replace every other expression that involves x. And looking quickly back at our problem, we had the antiderivative of, in the denominator, 1 plus the square root of x, but in the numerator, dx. So if we replace x right here with u squared, then we must also replace dx. Okay, so we need to, in our attempt to replace, we need to look at two things. If we're going to let x be equal to u squared, we must let dx be equal to 2u du. That is, the derivative of x is equal to dx. The derivative of u squared is 2u du. All right, making our substitutions. In place of dx, we've written 2u du. In place of x, we've written u squared. So really, what we have is the square root of u squared, which is simply u. And we don't know at this point whether or not we've helped. We theorized that the radical was giving us difficulty, so we tried to rid ourselves of the radical. Hopefully now we have something that we can integrate. So we go ahead and continue. We try to simplify, and this is what we get. We have the integral of 2u du all over 1 plus u. Now, this is a situation which you'll encounter many, many times. You must learn what to do in this situation. Anytime you have an expression whose denominator is a polynomial and whose numerator is a polynomial, where the numerator has a power that is equal to or greater than the power in the denominator. In this case, the powers are equal. They're both 1. Then in order to find the antiderivative, you've got to divide. So you need to divide 1 plus u into 2u. You won't be able to make any headway until you undertake that division. Undertaking that division, you'll get the integral of the quantity 2, this is the quotient when you divide, minus 2 over 1 plus u. This is the remainder. All times du. Okay, now continuing with what we already know of integration, breaking this into two separate integrals, we'd get the integral of 2 du minus the integral of 2 du over 1 plus u. Recalling that if we have constants, we can move those outside the integration symbol. We have 2 times the integral of du minus 2 times the integral of du over 1 plus u. Both of these integrations are easily performed. Integrating, we get 2u minus 2 times the log of 1 plus u, and we tack on the constant of integration. So we've been able to perform the task of integrating, but we're not through. Earlier I mentioned that we made a transformation in order to be able to perform our task, that in this case being that of integrating. We now have to return, go through the transformation in reverse, and put everything back the way we found it. Here the variable is u. In the original problem, the variable was x. So we must return to the variable x. So if we'll look back at our change of variable, we said we're going to replace x with u squared. Well, this tells us, if x is equal to u squared, that u is equal to the square root of x. So everywhere I have a u, I would have to put the square root of x. So our problem, after our integration was complete, gave us 2u minus 2 times the log of 1 plus u plus a constant of integration. So we would have 2 times the square root of x minus 2 times the log of 1 plus the square root of x plus c. If there is at any point doubt in your mind as to whether or not this is actually the antiderivative, if you were to take the derivative of this expression right here, then you should return to the original statement. You should be able to get dx over 1 plus the square root of x. Now, I'm not going to go through that on the tape, but if there's doubt in your mind ever about whether or not you've taken the antiderivative correctly, you can always check by taking the derivative. Now, in almost all cases, the thing that will encourage us to use a change in variable is a radical. Now, it isn't always so, but in a vast majority of the time, the thing that causes you to begin thinking about changing the variable is the presence of a radical that you cannot handle by using one of the formulas that you know. So most of the time when we change variables, it is to alleviate the presence of that radical. All right, let's look at example number 2 on your worksheet. Example number 2 says we want to find the antiderivative of the square root of 3 minus x all over x dx. Well, again, by ordinary means, we find that we can't take the antiderivative. It doesn't fit the power rule. Doesn't fit any of the other standard forms that we've studied to this point. So we began thinking that perhaps if only the radical weren't there, perhaps we could do something with the problem. So we actively set about to get rid of that radical. And we say to ourselves, if only that quantity under the radical had a perfect square root, we would be okay. We could take its square root and be rid of the radical. So we say, let's let 3 minus x be equal to u squared. All right, so we make the statement. 3 minus x is u squared. The one thing that we have to remember, though, is that we must be consistent. If we replace 3 minus x with u squared, everywhere we have an x or a dx, we must make the substitution. So solving this for x, we find that x is equal to 3 minus u squared, and a consequence of that, dx would be minus 2u du. So we return to our problem. In place of 3 minus x, we've decided to put u squared. That forces us to replace dx. So dx will be replaced with minus 2u du. That also forces us to replace x with 3 minus u squared. Making those replacements and simplifying, I'd get the integral of u times minus 2u du all over 3 minus u squared. Simplifying further, I'd get the integral of minus 2u squared du all over 3 minus u squared. Once again, the trick in going beyond this point is noting that both numerator and denominator are polynomials. They have equal degrees. So you must divide first. You must divide first. In dividing, I would get the integral of 2, this is the quotient, minus 6, that's the remainder, over the divisor, 3 minus u squared. All times du. Separating this into two integrals, I have 2 times the integral of du minus 6 times the integral of du over 3 minus u squared. This integral is easily handled. This integral can be handled in one of several ways. At this point, depending on the textbook you're using and the instructor you have, you may have already encountered a way of handling this. You may have encountered a formula. If you have learned it by formula, this is what your formula looks like. The integral of du over a squared minus u squared is equal to 1 over 2a times the log of a plus u over a minus u. The only thing we would have to do in order to use this form would be to put it into precisely this form. That is du over a squared minus u squared. It's already in that form with the exception of 3. And I would want to write it as something squared, so I could write this as the square root of 3 quantity squared. Now that still means 3, but I've written it as something squared. So it fits precisely this form. The antiderivative of this would be, moving just above it, minus 6 times 1 over 2a. So this would be 1 over 2 times a is the square root of 3 times the log of a plus u. Our a is the square root of 3 plus u all over a, which is the square root of 3, minus u. So if we choose to do this by formula, this is what we will get. Now, I mentioned that there are other ways to do it. There are other ways to do it. We could change the variable, but not by the means that I'm showing you. We could make a trig substitution here, but you may not have covered that at this point. We're going to have a tape on that particular topic. So we'll go ahead and take care of this antiderivative by formula. And of course this one can be taken care of easily. It's simply 2u. Now, I must return to the original variable. The original variable was x. I've been able to take the antiderivative, but my variable is u. and I've got to return to x. So I go back across and look. My substitution was this. It said we're going to let 3 minus x be equal to u squared. That tells me that u is going to be the square root of 3 minus x. So everywhere I have a u, I must put in the square root of 3 minus x. In doing so, I get 2 times the square root of 3 minus x minus, if we simplify this a bit, we note that 2 divides in to both numerator and denominator. I have 3 over the square root of 3. And if you wanted, you could rationalize the denominator, multiplying both top and bottom by the square root of 3. This would be 3 on the bottom. This would be 3 times the square root of 3 on top. Reducing, that would simply be the square root of 3 times the log of the square root of 3 plus u, which is the square root of 3 minus x, all over the square root of 3 minus u, which would be this. Now, this would be the antiderivative of the quantity we started with. It involves x. We've returned to the original variable, and at this point we would be through. Now, there are some other considerations. What happens when you have limits associated with your integral? What happens when you have the definite integral? Now, we're going to get to some examples that handle those situations in just a moment. Right now, let's move to example number 3. Example number 3. We're interested in finding the antiderivative for this expression. Once again, our first step is always to try to use some of the forms, the standard forms, the power rule in particular, that we've already studied. But as before, because of the radicals, we can't go any further. We don't know exactly what to do. So we find ourselves wishing, if only those radicals weren't there, perhaps I would have a chance. And so we're going to try to make a change in variable, and the change is going to be directed at ridding ourselves of these radicals. We have a square root and a third root involved, so whatever we decide to use in place of x must be something that has a perfect square root and a perfect cube root. So the choice is fairly obvious. We're going to want x to be something to the 6th power. So we say let x be equal to u to the 6th power. We must have a replacement for dx. dx, therefore, would be 6 u to the 5th du. Okay, returning to our problem, making our replacements. In place of dx, we have 6 u to the 5th du. In place of the square root of x, we have the square root of u to the 6th. In place of the third root of x, we have the third root of u to the 6th. Simplifying further, in the numerator we have 6u to the 5th du. In the denominator, u to the 3rd plus u squared. This is equal to 6. Constants can be moved out across the integration symbol. So we have 6 times the integral of u to the 5th du. Factoring u to the 2nd power out of our denominator, we have u squared times u plus 1. Reducing, we have 6 times the integral of u to the 3rd du over u plus 1. Again, our same situation has arisen. The power in the numerator is greater than the power in the denominator. That says divide. Dividing, we get 6 times the integral, the quantity u squared minus u plus 1. This is the quotient. Minus 1, that's the remainder, over u plus 1, which was the divisor. Breaking this up into series of separate integrals, we have 6 times the integral of u squared du minus 6 times the integral of u du plus 6 times the integral of du minus 6 times the integral du over u plus 1. Don't need this extra du out here. Carrying out each separate integral, we have 6 u to the third over 3 minus 6 u squared over 2 plus 6u minus 6 times the log of u plus 1 plus the constant of integration. We could go ahead and simplify further by reducing. This would give us 2u cubed minus 3u squared plus 6u minus 6 times the log of u plus 1 plus c. So we've completed our antiderivative. The only thing lacking is that our expression is still in terms of u. We need to replace u with something involving x. That is, we need to return to the original variable. So we go back to our original change of variable right here, and we note that x was equal to u to the 6th. Solving this for u, we find u would be equal to the 6th root of x. Now we could write it as the 6th root of x, or we could write it as x to the 1/6. This is strictly a matter of personal preference on your part. So we must go back now to the antiderivative involving u, and everywhere we have a u, we would put in the 6th root of x, or x to the 1/6 power. So this would be 2 times, in place of u, we have the 6th root of x, and that quantity is cubed, minus 3 times the 6th root of x, and that quantity is squared, plus 6 times the 6th root of x, minus 6 times the log of the 6th root of x plus 1 plus c. Now we could simplify this further, and as a matter of fact I do simplify this in your notes. I'm not going to take tape time in order to do this. Once again, the thing that started us thinking in terms of changing the variable would have been the radicals we encountered. The type of change we made was dictated by the type of radical and our attempt to get rid of the radical. After having made the change, found the antiderivative, we must return to the original variable. Okay, let's look at example number 4. Here we're interested in finding the antiderivative of x times the cube root of 1 plus x dx. And as before, we try everything we know first. We cannot make any headway. We cannot find the antiderivative. So we attempt to get rid of the radical. We have the third root involved, so we want something to replace 1 plus x that has a perfect third root. So the natural choice would be 1 plus x is equal to u to the third power. That says x would be u to the third power minus 1. That says dx would be 3u squared du. Making the substitutions. In place of u, in place of x, u to the third power minus 1. In place of 1 plus x, u to the third power, we're going to be taking its third root. In place of dx, 3u squared du. Simplifying, we have u to the third minus 1 times u times 3u squared du. Multiplying, we get 3u to the 6th minus 3u to the third quantity times du. Breaking this into separate integrals, we have 3u to the 6th du minus 3 times the integral of u to the third du. Carrying out the integration, we get 3u to the 7th over 7 minus 3u to the 4th over 4 plus c, the constant of integration. Replacing u, we note in our original statement that 1 plus x was u to the third power. Therefore, u would be the third root of 1 plus x, or we could have written it as 1 plus x to the 1/3 power. Either way you want to do it is fine. Replacing u, we have 3 times the cube root of 1 plus x. This quantity is raised to the 7th power, all over 7. minus 3 times the third root of 1 plus x raised to the fourth power quantity over 4 plus c. If you want to use radicals, that's fine. Personally, I usually use exponents. To me, that seems the easier way to go. That is a matter of personal preference. If this were changed to an exponential expression instead of a radical expression, this would be 1 plus x to the 7/3. And this would be 1 plus x to the 4/3. Making those changes, factoring out 1 plus x to the 4/3 times 3, I would get this, which could be simplified to this form. The constant of integration would appear since that I didn't have limits involved. Okay, let's move to example number 5. Example number 5. Here we're interested in finding the definite integral of x times the square root of 8 minus x dx. And the limits are 0 to 8. That says x ranges from 0 to 8. Well, in finding the definite integral, I first of all must take the antiderivative, and then having taken the antiderivative, I then consider the limits. The antiderivative is a little bit difficult to take. We can't take it by standard means. We don't have a form that fits this particular expression. So we again think about getting rid of the radical. We replace 8 minus x with something having a perfect square root. Therefore, we say let 8 minus x be u squared. That says x will be 8 minus u squared, and dx will be minus 2u du. We make our replacements. 8 minus u squared is used in place of x. In place of 8 minus x, we put u squared. We take the square root of that, we get u. In place of dx, we get minus 2u du. Now, we have changed the variable. We have changed the variable from x to u. These limits were for x. These limits say x ranges from 0 to 8. They are not the same limits for u. Now, at this point, I suggest that you find the limits for u. It's possible to work this problem without finding them. I recommend to my students that they go ahead and find the limits for u. They're not difficult to find as a rule. Looking back here at the expression we used for the change of variable, we see that x is equal to 8 minus u squared. And so we say, if x were 8, 8 being our top limit over here, if x is 8, what is u? Okay, if x is 8, then here's our expression. We replace x with an 8. Solve this equation for u. That says minus u squared is equal to 0, and that says u would be 0. So when x is 8, u is 0. So that must be my top limit right here. When we had the variable x, the top limit was 8. When we have the variable u, the top limit is 0. When x is 0, that's our lower limit. Making the same substitution, we have 0 is equal to 8 minus u squared. That says u squared would be 8. And that says u would be the square root of 8, which is 2 times the square root of 2. So our lower limit would be 2 times the square root of 2. When x is 0, u is 2 times the square root of 2. Now, I have my new limits for u. whether I elect to use them or not isn't it important right now. What is important is that I go ahead and find the antiderivative. I'll have an option as to whether or not I use these limits in just a minute. So finding the antiderivative, I multiply all of these factors together, and I get the integral of minus 16u squared plus 2u to the fourth, quantity times du, where the limits are 2 times the square root of 2 to 0. Finding the antiderivative, a term at a time, minus 16u to the third over 3 plus 2u to the fifth over 5. The limits are 2 times the square root of 2 to 0. Now, at this point, if I want to use these limits, I can. If these limits are fairly nice numbers, I would probably go ahead and put these limits in place of u. I don't have to do that. If these limits turned out to be fairly difficult ones, numbers, perhaps you don't like to work with radicals, and this may not be a suitable limit for you. I have the option of replacing u with x and then returning to the original limits, 0 and 8. Or I have the option of leaving this as u and working with these limits. I can go either way. I'm going to show you both ways for this reason, not because I think you ought to use both ways, but to convince you that regardless of which way you go, you get the same number. This is the definite integral. You will get a number, not an algebraic expression. There's a difference between antiderivative and definite integral. This is the definite integral. This will provide you with a number. All right, so if we continue letting the variable remain as u, we must use these limits. All right, putting in the top limit, I have minus 16, 0 to the third over 3, plus 2 times 0 to the fifth over 5. And you can see that this is going to be simply 0. Minus 16 times the lower limit, 2 times the square root of 2 cubed all over 3, plus 2 times the square root of 2 raised to the fifth power all over 5. Now there are lots of ways to simplify this. You don't have to use my method. Anytime I can work with powers of a number, I do it. 16 is 2 to the fourth. Cubing this, I get 2 to the third. The square root of 2 is 2 to the 1/2. You can see I have a definite tend toward using exponents rather than radicals. 2 to the 1/2 when cubed would give me 2 to the 3/2. So this is 2 to the fourth, 2 to the third times 2 to the 3/2. Doing the same thing over here, this is all over 3. Doing the same thing over here, I have 2 times 2 to the fifth times 2 to the 5/2, all over 5. So continuing with my multiplication, multiplying these together, you add exponents, I get 2 to the 17/2 all over 3, minus 2 to the 17/2 all over 5. I could factor out 2 to the 17/2, and this would give me 2 to the 17/2 times 1/3 minus 1/5. When I simplify 2 to the 17/2, there are several ways to think of this also. Again, how you do it isn't as important as the final result. 2 to the 17/2 is the square root of 2 to the 17th, and that's 2 to the 8th times the square root of 2. That's what I have here. 2 to the 8th times the square root of 2 times 1/3 minus 1/5. 2 to the 8th times the square root of 2. Subtracting here, I get 2/15. Bringing the 2 out and multiplying it times 2 to the 8th, I get 2 to the 9th times the square root of 2 all over 15. This is the definite integral. It is a number. It is not an algebraic expression. The point that I think you must understand is that had I, back over here, had I decided to return to the variable x and use the limits for x, I would have gotten exactly the same number. All right, as evidence of that, let's move right over here on the far board. I have minus 16 u to the third over 3 plus 2 u to the fifth over 5, the limits for u. 2 times the square root of 2 to 0. I'm going to return, and I'm going to replace u with what it is in terms of x. So all the way back across the board, right here. 8 minus x is u squared. That says u is the square root of 8 minus x, or if you wish, that's 8 minus x to the 1/2. Everywhere I have a u, that's what I replace it with. Okay, returning to our problem. I have. Now, if you want to take this a step at a time, this is 8 minus x to the 1/2 quantity raised to the third power. This is 8 minus x to the 1/2 quantity raised to the fifth power. But that means, using your laws for exponents, that this will be 8 minus x to the 3/2 power. And this will be 8 minus x to the 5/2 power. The limits are for x. The limits go from 0 to 8. I put in the top limit of 8. Putting 8 in place of x, I have 8 minus 8, which is 0. So I have minus 16 times 0 to the 3/2 all over 3. Plus, replacing x with 8, 8 minus 8 would be 0. So I have 2 times 0 to the 5/2 over 5. Minus, putting in the lower limit, which is 0. I have 8 minus 0. So this becomes minus 16 times 8 quantity to the 3/2 all over 3, plus 2 times 8 minus 0, which would be 8 to the 5/2 all over 5. Now, if you wanted another name for this, I have 8 to the 3/2. This is 8 to the 1/2 cubed. That's the square root of 8 cubed. That's 2 times the square root of 2 quantity cubed. Now I write it this way simply to make it look like the other one looked a moment ago. I have 16 times 2 times the square root of 2 cubed minus 2. I can do the same thing here. 2 times the square root of 2 to the 5th all over 5. Now I'm not going through the simplification again, but compare this with what we had right over here. It's the same thing. From here on, the simplification is the same. I'll get 2 to the 9th times the square root of 2 all over 15. Regardless of which way you go, regardless of which set of limits you choose to use, you'll get the same number. The option is yours. The thing that causes you to decide one way or the other would be the complexity of these limits. If these are fairly easy numbers to use, 2s, 3s, whole numbers, then probably you would elect to keep them and use them. If these numbers turn out to be difficult numbers with complex radicals, you would probably elect to go back to your original limits. The choice is yours. Either way, you get the same result. All right, let's move to example 6. Example number 6. We're interested in finding the antiderivative of e to the 3x dx all over the square root of e to the x minus 1. Once again, the first thing we try is to make this fit conventional formulas, especially the power rule. If all else fails, then we might consider trying to get rid of the radical. If we do want to get rid of the radical, we would want to let e to the x minus 1 be something with a perfect square root. So we let e to the x minus 1 be equal to u squared. Now, to be consistent, we have to replace x everywhere with this particular substitution we've decided on. That means that we've got to solve this equation for x in order to get our hands on dx. So e to the x is u squared plus 1. We're interested in solving for x. This is an exponential equation. You take the log of both sides. Log e to the x is equal to log u squared plus 1. One of our rules for logarithms says we can shift this down into this position. We have x times the log of e equal to the log of u squared plus 1. The log of e is 1. So we have x equal to the log of u squared plus 1. Therefore, dx, the derivative of this side, would be equal to the derivative of this side. That says dx is 2u du all over u squared plus 1. Now, we go back and make our replacements. One adjustment we might make to make this perhaps easier to work with is to notice that e to the 3x means e to the x quantity cubed. Using your rules for exponents, if you multiply, you get e to the 3x. So we have e to the x quantity cubed dx all over the square root of e to the x minus 1. Making our replacements. In place of e to the x, we use u squared plus 1. So we have e to the x to the third, in other words, u squared plus 1 to the third. In place of dx, this is dx, we have 2u du all over u squared plus 1. In the denominator, in place of e to the x minus 1, we put u squared. So we have the square root of u squared. Simplifying, we have u squared plus 1 quantity to the third times 2u du all over u times u squared plus 1. Dividing u squared plus 1 into top and bottom, dividing u into top and bottom, I get u squared plus 1 quantity squared times 2 du. Our job is to find the antiderivative of this. If it doesn't fit a form, then we can certainly try to make it fit a form. If we go ahead and square this quantity, we'll be able to find the antiderivative. Bringing the 2 out in front of the integral and squaring, we get u to the fourth plus 2u squared plus 1 quantity times du. Finding the antiderivative of each of these terms, we get 2 u to the fifth over 5 plus 4 u to the third over 3 plus 2u plus c. So the antiderivative has been taken. The only thing we need to do now is to return to x. So if we go back and look at our original substitution, e to the x minus 1 was u squared. This says that u is equal to the square root of e to the x minus 1. So everywhere we have a u, we can put the square root of e to the x minus 1, or e to the x minus 1 quantity to the 1/2, whichever you prefer. Putting it in, we have 2 times, I've used e to the x minus 1 quantity to the 1/2, raised to the fifth, all over 5, plus 4 e to the x minus 1 to the 1/2 quantity to the third, all over 3, plus 2 e to the x minus 1 quantity to the 1/2 plus c. If you wanted to simplify your exponents a bit further, you have 2/5 e to the x minus 1 to the 5/2 plus 4/3 e to the x minus 1 to the 3/2 plus 2 e to the x minus 1 to the 1/2 plus c. Now in your notes, I've carried the simplification further. I'm not going to take tape time to do this at this time, but you could go further in your endeavor to simplify this. Okay, let's look at example number. Example number 7. We're interested in finding the antiderivative of dx over the square root of x plus 1 minus the square root of x. Again, we try all the different forms we know. We try to make it fit the power rule. We pretty well come up empty. We don't find anything that fits this form exactly. And so we're tempted to say, well, since we have radicals involved, maybe we should try to make a change in variable. I present this problem simply to try to culture your thinking along these lines. Just because a radical is there that you don't know how to handle doesn't mean that a change of variables is the way out. Does not mean that. Oftentimes, when a radical is present, if you can juggle things algebraically, you'll find that it will fit one of your forms. So don't give up too quickly on trying to rearrange this before you appeal to a change of variable. If you can see a change of variable immediately that will do the job for you, it's all right to go to it. But in this case, there isn't a change of variable that's obvious that will rid your expression of the radical. One of the things that you can try, this is an algebraic trick, it's one that you use a lot, and that's to get rid of the radical on the bottom. Rationalize the denominator is the way it's expressed in algebra. To do this, we would multiply both top and bottom of the expression by this plus this, often called the conjugate of it. Okay, so let's see what happens when we do this. Multiply top and bottom by the square root of x plus 1 plus the square root of x. Multiplying on top, we get the square root of x plus 1 plus the square root of x dx. On bottom, we get the product of these two, the square root of x plus 1 quantity squared minus the square root of x quantity squared. We get on top square root of x plus 1 plus the square root of x all times dx. On bottom, we get x plus 1 minus x. So simplifying, the denominator becomes 1. We can break this up into two integrals. I've rewritten it using exponents. We have the integral of x plus 1 to the 1/2 dx plus the integral of x to the 1/2 dx. Integrating, taking the antiderivative, we get x plus 1 to the 3/2 over 3/2 plus x to the 3/2 over 3/2 plus the constant of integration. And then simplifying a bit further, 2/3 x plus 1 to the 3/2 plus 2/3 x to the 3/2 plus c. The point is, a change of variable is not always the answer when you have a radical that you think you can't handle. Don't give up on the algebra too quickly. Try to simplify it. Try to make it fit one of the other forms. Perhaps it will work. Now, the key things to remember when you're thinking about a change in variable, oftentimes when you see a radical that you cannot handle, this means that a change of variable might be the way out. Remember, when you change the variable, if you're changing from x to u, you must change all x's, not just a portion. Every x must be replaced with something involving u. If you're working with a definite integral and you have limits that pertain to x, if you change the variable, then you need to change the limits also and at least look and see if those limits are nice enough to be usable. If they're not, you can always, after finding the antiderivative, return to the original variable and use the original limits. If you're finding only the antiderivative, the indefinite integral, where no limits are present, remember, when you change the variable and find the antiderivative, you must return to the original variable. You're not through until you return to that original variable. Always try to simplify your answers. If you have difficulty in your homework assignment making your answers match the author's, you might spend a few minutes studying the simplification in the notes of some of the answers that I have. Most of the time, your work is made easier if you'll use exponents.